You know, why don't you fall through the floor? Coffee cup turning into a donut and back again, because education will professors and people will never get replaced by AI robots. I kind of like chemistry because it was kind of mixing chemicals together and colors change, or you make explosions or something like this. Go to some meeting, you spend your time. You don't have to be Einstein to get a Nobel Prize. Physics can be a very dry subject. In fact, it's a very beautiful subject. Hi Billy. I'm Duncan Haldane. I won the Nobel Prize for Physics in 2016 and I work on cool stuff in quantum mechanics. Billy, cheers!
请开始你的表演。这个是访问，你想知道的都有。
It's not quite easy for people to understand fundamental researches such as topology. Could you introduce what is topological phase transition and the topological phase of matter?
Of course, it is very difficult to explain. What's happened is that quantum mechanics has always been a very mysterious subject, right? It's very, if you think too hard about it, it makes your brain hurt. Well, those are very complicated words. They really represent kind of unexpected things in quantum mechanics and in the properties of superconductors. People were confused about and turned out to have a very beautiful relation to the mathematics of topology, which is a very abstract idea about the shape of things, but has a very simple mathematical description. All the time in our field, an experimentalist wants to introduce his work, but he always will show a picture of a coffee cup turning into a donut and back again, because topologically speaking, a coffee cup and a donut are the same thing. They both have one hole through them. And topology is about counting the number of holes in a surface, and basically holes come in whole numbers. You can't have 0.5 of a hole, or holes are either one hole, two hole, three holes, and you can't go continuously from one hole to three holes or two holes. If I take Billy here and I want to, I would have to poke very hard at him to make a hole come through. And so there's a stability in these things which are counted by whole numbers, that they're resistant to destruction. You can change them, but you have to try hard, and that's why this topological stability of states in quantum mechanics, which was kind of surprising, is people now believe that they could use this to solve one of the big problems in quantum computers, which is the stability of the information that you put into them, and which can become lost by interaction with the environment. So that's the big problem in quantum computers. On paper it works perfectly. In practice it's very delicate, and if you can protect it, then that would be the key to make this whole thing work. These first wave of implementations of quantum technology, they're unprotected. They don't have, the word is called noisy intermediate scale quantum technology. So you're trying to make the quantum process the information using quantum mechanical methods and algorithms, but you're always at risk of losing the calculation before it finishes. So with noisy intermediate scale things, which are the first qubits people are making, you have to basically repeat the calculation many times, and if you get the same answer twice or three times, you can say, well, that wouldn't have happened unless it worked, right? But so far the idea, but the conceptual idea of the topological protection of information is very beautiful on paper, but it hasn't happened yet. There are all kinds of questions about, is quantum mechanics compatible with free will? Does it describe the universe? Those are very abstract questions, but people have worried. There's a lot of people worry about it, but as a practical quantum mechanic, we know it works for describing matter on small scales, and so you look around you and you can't see. Initially, you can't see quantum mechanics, but why don't you fall through the floor? Your atoms are almost 99.9% empty space, and it turns out it's the quantum mechanical principle that two electrons can't be in the same place that prevents you from gravity from just pulling you into the center of the Earth. Now, Newton just described that as it seemed like an obvious force. You push on something, it pushes back. The only reason that happens is because of quantum mechanics. Coming to the conclusion that quantum mechanics is the true description of the world around us. But it's very difficult to make contact with every day.
For average people, how do we get started? What is the best way towards quantum mechanics?
I think the most important thing for people certainly to get involved in STEM activities, I think, is high school and mathematics. The most important thing for creating new scientists is the teacher. I never liked physics at school, and I kind of liked chemistry because it was kind of mixing chemicals together and colors change, or you make explosions or something like this. And the last year there was a very good physics teacher and who was enthusiastic, and I've talked with many other people. Pretty well everyone has some story about some particular teacher at the school inspired them. The ones who managed, the inspirational ones are the ones who managed to ignite the passion for science. Physics can be a very dry subject, you have to learn about some lever but yeah, in fact it's a very beautiful subject and people get very passionate about it. I guess regular people can't understand why people get passionate about it, but the way you can find such simple and profound descriptions of nature in a few equations is always impressive to young people, I think.
What's your most interesting area on the frontier of physics?
Well, I guess understanding these issues in quantum mechanics. My current theme is actually quantum geometry. We had quantum topology before, so it sounds like another branch of mathematics. But they're very intriguing. Physics is a very unified subject. It turns out that probably because quantum mechanics applies both from the small scale to the large scale. So quantum geometry is something that people are worrying about for theories of quantum gravity, and at least there's a few analogies with this in some of these interesting low temperature systems I look at. There are lots of puzzles, and I think that's the challenge that really everyone wants to kind of solve a puzzle. Right? There's probably too much competition now for all the young people who've got much more energy than me to push things forward.
You said you have a gap of 9 months before you started university. During the time, you traveled to some Middle East countries. After you have become a professional physicist, you got a chance to come back to those countries. Have you found anything new about these trips?
Well, if you go professionally, you're always going to some meeting, you spend your time talking physics, and maybe there's one outing to see some cultural thing. So it's quite different.
You've also visited China before. What do you think about the development of basic science here in recent years?
Well, I think China has just really taken off. For example, to get a Nobel Prize, there has to be an experimental verification. And for example, one of the two things that I did that was cited, it took 25 years for it to become realized in practice, and it was actually realized in practice by the group at Tsinghua University. This was called the quantum anomalous Hall effect. It was something that before you needed huge magnetic fields to see it, and then I came up with an idea that it actually could be done with magnetism rather with magnetic fields. As I say, it has been very difficult to get in all these things. Material science, what we can do nowadays is really create new materials for the specific physics, right? Yeah. To do something special, and in fact, the beautiful materials for this were created at Tsinghua. A very interesting experiment. The laboratories I visited in China, the young people have top quality equipment now, and in 1988 it was a different matter. There was, but in 2018 and 19. There's a lot of going on in the laboratories in China.
Looking back upon your academic career, what do you think is the most important quality of doing research? Any advice to young scientists?
Yeah, I think the most difficult thing, or the important thing in any scientist's career, whatever, is to learn how to think, right? Which is really, because the problem in science is to find the right question. Because you look around, there's some new phenomena, it's not at all clear what exactly the problem is, how to understand it, what questions to ask. And once you find the right question, the answer is much more technically easy to find. And if something interesting or something odd appears, if you try and investigate it a little bit, it may just turn out, most of the time it'll be some curiosity, but very occasionally it might be something really big. And none of the things I did were deliberate. I wasn't planning to find something, but luckily my path, probably because I was coming from a slightly different direction from other people in that area, my path took me to a place where suddenly I could see that there was something different, right? So I think anyone working in basic research, you don't have to be Einstein to get a Nobel Prize. You have to be lucky, and you have to be able to exploit your luck, and you probably have to be able to fight for to get people to believe what you've found. You need to be able to take a little detour to look at anything unexpected and interesting that you run across. I think I was helped tremendously by being fortunate enough to find good mentor. I learnt a lot from my mentor, Philip Anderson, who was also a Nobel Prize winner. But I think wherever you are as a young scientist, I think you should seek out who you can learn from, and it's really learning how to look at things rather than not learning technical details, but learning so I gained a lot from just talking with him, because he actually didn't help me very much with the problem he gave me. I would go in to try to tell him about what I was trying to do, but he would tell me about what he was interested in that day, and it was always very... So that's why I think education will professors and people will never get replaced by AI robots, You might say you could just, if it's just a question of listening to lectures, you could just take a movie of someone giving a very good lecture. But I think if the students just watch this movie, it'll go in one ear and come out the other ear. It won't. You can't learn that way. You can really have to learn by personal interactions with people. So.
take it easy, just relax.
Thank you.
You can sit. You sit.
I can sit on Billy. Or I should put him behind me.
Yes.
Okay.
More polite.
Yes.